Hello everyone, this is the first lecture in the series of lectures on real analysis, and in this lecture we're going to discuss the set of real numbers R as a field, and in particular we are going to cover the field axioms and the properties of R derived from the field axioms. So before we proceed any further, let us discuss some notation. So let us discuss some basic sets. The set n consists of the numbers 1, 2, 3, and so on. It is the set of natural numbers. The set z is the set of all integers, 0, 1, 2, negative 1, negative 2, and so on. Q is the set of all rational numbers, so it's the set of all quotients, p over q, where p is an integer and q is a natural number. And then finally R is the set of all real numbers, and we are going to discuss in more details about what the set of real numbers is. And we are going to actually have several lectures about what R is. Now let us discuss some basic notation. So this upside down letter A, it means for every, and it is derived from the word any. If you take the first letter of the word any and write it upside down, you will get this quantor. So this is a quantor. This is a quantor. So then the next quantor that we will consider is exists. So it is taken from the word exist from the first letter, and it's just the letter is mirrored. Then the next quantor is belongs to or in. If we write exists and exclamation mark, that means exists unique. ST stands for such that, so this is not a quantor, this is just an abbreviation. This double arrow here, it stands for implies, and this arrow that points in both directions, it stands for if and only if. So let us consider some examples of how to use quantor notation. So this sentence right here, this statement, we can say that for every x in the set of natural numbers, x is greater than or equal to 1. So it basically says that every natural number is greater than or equal to 1. And since the natural numbers are 1, 2, 3, and so on, this is true. So this statement right here, the next one, we can read as there exists x in z, so an integer x, such that x squared equals to 4. So of course 2 squared is 4 and negative 2 squared is 4, so there definitely exists an integer which is either 2 or negative 2, that such that when we square it we get 4. The next statement we can read is as follows: there exists a unique x in z such that x plus 7 is equal to 4. And definitely there exists the only x such that x plus 7 is equal to 4 is negative 3. So, and that's a unique x. So the next one, this statement we can read as x less than 5 implies that x squared is less than 25. We are going to discuss the properties of real numbers that justify this implication. This is definitely true. And then x is less than 5 if and only if x plus 2 is less than 7. So if we look at this inequality x less than 5, and if we add 2 to both sides of this inequality, we will get that x plus 2 is less than 7. On the other hand, if we start here and look at this inequality x plus 2 is less than 7, and if we subtract 2 from both sides of this inequality, we will get x is less than 5. So this implication is in both directions. X less than 5 implies x plus 2 less than 7, and x plus 2 less than 7 implies x less than 5. So this is why we write if and only if, because both implications are true. So the set of real numbers R, it satisfies the following axioms. So first of all, R contains the set of rational numbers. Then R is a field. R is an ordered field, and R is complete. So we have not discussed yet what it means that R is a field. And we have not discussed what it means that R is an ordered field. We have not discussed yet what it means that R is complete. This is always coming. So the first order of business is to define a field. So DF stands for definition. So a field is a non-empty set F with operations plus and multiplication on it that satisfy the following axioms. So there are 7 axioms of a field. We denote them by field axiom 1, field axiom 2, and so on, field axiom 7. And so just in case you were wondering what F cross F stands for, like here in this notation. So F cross F is a Cartesian product. It's the set of all ordered pairs A, B, such that A and B are both in F. And so plus F cross F into F, it just means that to every ordered pair AB such that AB are in F, the operation plus puts in correspondence the element A plus B. Okay, so that's all that this notation means. All right, so let us discuss the field axioms. So the first field axiom is commutativity. This field axioms means that if we choose elements A and B in the field F, then A plus B is B plus A. So the order in which we write the elements when we add them, it doesn't matter. And A times B is B times A. The next axiom is associativity. So for every triple of elements A, B, and C in F, A plus B plus C is the same as A plus B plus C. So the order in which we add, when we add 3 elements, it doesn't matter. And similarly for multiplication, A times B times C is A times B times C. Now the next axiom is existence of additive identity. So this axiom means that there exists a 0, an element of F, such that when we add 0 to an element A of F, nothing changes. So A plus 0 is equal to A for every A in F. The next axiom is the existence of additive inverse. So for every A in F, there exists an additive inverse which we denote by minus A in F, such that A plus minus A is equal to 0. So to be an additive inverse, it means that it's an element such that when you add it to A, you get 0. The next axiom is the existence of multiplicative identity. So there exists a 1 in F such that 1 is different from the additive identity. So 1 is not equal to 0, and when we multiply an element A of F by 1, nothing changes. We get A. So A times 1 is equal to A for every A in F. The next axiom is the existence of multiplicative inverse. So for every A in F, such that A is not equal to 0, there exists A inverse in F such that A times A inverse is 1. So to be a multiplicative inverse, it means that it's an element such that when we multiply it by the element itself, we get 1. The next axiom is distributivity. So for all A, B, C in F, A times B plus C is A times B plus A times C. All right, so these are the 7 axioms of the field. And so now you can believe that R is a field from your intuitive understanding of the set of real numbers that you have from working with numbers. You may notice that all of these axioms are satisfied by real numbers. So now the question in this example is N a field, is Z a field, is Q a field? So as far as N is concerned, N is not a field, and here is why. So for example, 5 is an element of N. So then by the field axiom 4, if N was a field, then we would have that minus 5 would be in N, but minus 5 is not in N, so therefore N is not a field, because it doesn't contain the additive inverse of 5. Now, as far as Z is concerned, Z is not a field either, because 5 is in Z. However, 5 inverse, which is 1 over 5, it's not an integer, so it's not in Z. So therefore Z is not a field. As far as Q is concerned, the set of all rational numbers, Q is a field. And I'm going to leave it to you as an exercise to verify that all the 7 axioms of the field are true for Q. So as a remark, the operation plus is called addition, the operation times is called multiplication in the field axioms. Then when we write A, B without anything in between, that means A times B. A minus B stands for A plus negative B. 1 over A stands for A inverse, and B over A stands for B times A inverse. And then let us define what is a subfield. So a set Q is a subfield of a field F if Q is a subset of F and Q is a field. All right, so we have discussed the field axioms. Let us now discuss the following theorem. It turns out that from the field axioms, we can derive many more properties. And so there are 8 properties in this theorem that we can derive from the field axioms. So let F be a field, then the following holds. The additive identity is unique. So 0, there is only one 0 in the field F. And there is also only one 1 in the field F. So is the multiplicative identity. Now the next property that we can derive from field axioms is that additive inverse of each element of F is unique. And also the multiplicative inverse of each non-zero element of F is also unique. The next property is that for every A in F, 0 times A is equal to 0. So field axioms imply this property. The next property is that for every A in F, when we take -1 and multiply it by A, we get -A. So the real meaning of this equality is that when we take an additive inverse of 1 and multiply it by A, we get an additive inverse of A. The next property is that for every A and B in F, A times minus B is the same as minus A times B is the same as minus AB. So it means that A times the additive inverse of B is the same as additive inverse of A times B is the same as additive inverse of AB. The next property is that for every A in F, minus A is A. So the additive inverse of the additive inverse of A is A itself. The next property is that if we have two elements of F such that their product is equal to 0, so if A, B is in F's are such that A times B is equal to 0, then A is equal to 0 or B is equal to 0. And the last property in this theorem is that if we have three elements A, B, and C in F, and if they are such that A plus C is equal to B plus C, then A is equal to B. So we are not going to prove every single property in this theorem, but we will prove just a few so that we get a flavor of how to prove other properties of the field from the field axioms. And you may have noticed that all of these properties sound familiar. They are all satisfied by real numbers. And that is not surprising because the set of real numbers is a field. So therefore, all of these properties are true for real numbers. Okay, so let us prove the first portion of the property I. So we want to show that the additive identity of the field F is unique. The additive identity of F is unique. So how do we do that? So let us assume that there are two additive identities. So suppose that 0, 1 and 0, 2 in F are additive identities. What we want to show is that 0, 1 is equal to 0, 2. So that would mean that additive identity is unique. So let us go ahead and try to show this. So 0, 1 is equal to 0, 1 plus 0, 2. And why is that? Is because 0, 2 is an additive identity. So if we add it to 0, 1, we do not change anything. But by commutativity, it is 0, 2 plus 0, 1. And we know that 0, 1 is an additive identity. So when we add 0, 1 to 0, 2, we do not change anything. So therefore, this is equal to 0, 2. So hence, 0, 1 is equal to 0, 2. And this is how we prove that the additive identity is unique. So I leave it as an exercise to you to prove that the multiplicative identity is unique. The proof is very similar. So QED. So now let us prove the property II. So the property II states that the additive inverse of each element of F is unique, and the multiplicative inverse of each non-zero element of F is unique. So we are going to prove only the first portion of statement II. So let A be an element of F. What we want to show is that the additive inverse, which is minus A, is unique. So again, to show that it is unique, let us assume that there are two of them. So suppose that A1 and A2 are additive inverses of A. So what we want to show is that A1 is equal to A2. Okay, so A1 is the same as A1 plus 0, because when we add 0, we do not change anything. But 0 is the same as A plus A2. So let us think about this for a moment. So A2 is an additive inverse of A. So when we add A2 to A, we get a 0. Right? This is equal to 0 because A2 is an additive inverse of A. So now by associativity, this is the same as A1 plus A plus A2. However, A1 is an additive inverse of A. So when we add A1 to A, we get 0. So this is equal to 0 plus A2, which is A2. So A1 is equal to A2, just as we wanted to show. And I'm going to leave it to you to show that the multiplicative inverse of every non-zero element of F is unique. The proof is very similar. QED. Now let us prove the property III. So let us recall what that property is. So the property III is the following. For every A in F, 0 times A is equal to 0. So let A be an element of F. We want to show that 0 times A is equal to 0. So let us observe the following. So if I take A and add to it 0 times A, this is the same as 1 times A plus 0 times A, because when we multiply A by 1, we do not change anything. But then by distributivity, this is the same as 1 plus 0 times A. But 0 plus 1 is equal to 1 because when we add 0, we do not change anything. So this is the same as 1 times A, which is A. Right? So A plus 0 times A is equal to A. So A plus 0 times A is equal to A. So somehow from this, we should be able to show that 0 times A is equal to 0. So 0 times A is equal to 0 times A plus 0 which is 0 times a. And instead of 0, we are going to write a plus minus a, right? Because a plus minus a is equal to 0. Now, by distributivity, we can change parentheses as follows. So this is 0 times a plus negative a. But we have just shown that a plus 0 times a is equal to a. So this right here is equal to a. So then we get a plus negative a, which is 0. So hence, 0 times a is equal to 0, just as we wanted to show, QED. So by the way, QED stands for quod erat demonstrandum. Which means this is what we wanted to show. All right, this is the end of this lesson here. So we just proved three properties of the field in this theorem. I leave all of the other properties in this theorem for you as a homework to show, to prove from the field axioms. And in the next video, remember we said that R is a field, and then we said that R is an ordered field. So in the next video, we are going to discuss what is an ordered field. And then in the video after that, we are going to talk about what it means that R is complete. So this is all for now. Please support this channel by subscribing to it. Put a like under this video. And be good at math.